Peter. It's great to be here. As Peter mentioned, I'm from Snowflake, where I had the pleasure of working with Martin for about the last 10 years. So when I was asked to talk here, I thought it was kind of a good opportunity to look back at the choices that we made when we architected Snowflake, the reasons that we decided we needed to build this new system, how we built it, the decisions we made in the early days, and how they ended up impacting the capabilities of our system. Okay, thank you. All right, so I'm going to give a little bit of an overview about Snowflake, answer some of those questions about why did we do this, tell you about our architecture, and then I will talk about kind of 3 areas where the architecture has made our system more capable. So first, a little bit about Snowflake. So our mission is to enable every organization to be data-driven. It's a lofty mission, but I think it's something that's close to all of our hearts, so I probably don't need to explain the motivation behind that. But today, maybe people don't ask, like, why are you starting this company and building this new database? But back 10 years ago, it was a pretty common question for people to ask, why are you building a new database? There are a lot of database systems out there. As I think Andy mentioned, most people at the time were like drinking the Hadoop Kool-Aid, so it was considered a little crazy. So I thought I'd tell you a little bit about what our answer was way back then. So we saw a lot of changes in the data landscape. There was more data out there to analyze. More and more data was machine generated. Most of the time that I was at Oracle, when we talked about data warehousing, we were talking about operational data stores, OLTP systems that were then kind of dumping their data into a data warehouse for analytics. And that was really shifting into lots of machine generated data. And that meant there was way more data. It wasn't necessarily as well structured, so semi-structured data was becoming very popular. You had more and more users, more types of people within a company whose jobs really relied on data. And you had kind of, because of those different types of data personas, you also had kind of different needs in terms of, do I need really quick responses, kind of more real-time analytics versus the batch analytics of earlier times. And as I mentioned, just a lot more diversity in terms of where data was coming from. It wasn't just coming from your OLTP systems. It wasn't necessarily just coming from your systems. It could be coming from systems that other organizations owned. So this was all happening while the cloud was coming into being. And cloud computing kind of promised to us a lot more elasticity. You can kind of pay as you go, use more resources when you need them, don't use them as you don't. You don't need to build out this huge data center inside your own organization. You can kind of rent time on somebody else's. And this seemed to go very well with the explosion of data and the explosion of data processing needs. But at the same time, it didn't really seem like the systems that existed at the time were really well adapted to the cloud ecosystem. And so that was what motivated us to start Snowflake. So Snowflake was started in 2012. Martin joined as the 3rd founder a few months later. I joined a few months after that. And now I'll tell you a little bit about the decisions that we made in those early days. All right, so first let's talk a little bit about analytics in the pre-cloud era. I have this cute little picture here, which is kind of an abstract notion of what you might be doing in your data warehousing system at any given time. So each colored line is a different workload. It might be a different department in your company is running a different workload. If you look at this over time, some of the workloads kind of spike in terms of the resources that they need. Some of them, grow kind of nicely. Some of them, change abruptly. You might imagine that the green line, for instance, is a data load, which kind of wakes up, happens every now and then goes back to sleep. Other things that kind of go up and down might go up and down based on kind of business hours, because maybe there's like a real person behind the query that's generating that load. So in the days of on-premises computing, a company would essentially own a cluster of computers, own a data center, and they would pay for some software from a database vendor, install it on their cluster, and these were the resources that were available to run their analytics. Changing resource capacity was really expensive. Most companies did this on the every 3 years or so granularity. And so that meant that all of these departments with all of these resource needs were kind of competing for what was available. So how did they do it? So like I said, there's a collection of workloads. Each workload has its own demands, and so it's kind of a resource optimization problem. Or in an ideal world, it's a resource optimization problem. So each workload yields some value. Finance has their workloads, HR has their workloads, et cetera, et cetera. Workloads that generate money for the company probably have greater value. So you want to find a resource allocation that maximizes ROI. Like I said, this is in a ideal situation. In reality, it would be more likely that the IT department, when they had to buy this new analytics system, would kind of decide how many resources they probably needed for the next N years. Once they had them, the department that screamed the loudest would get the most time. But as a result, they would have to decide that for some ROI level, it was worth running and for the amount of resources available, it's worth running your workload. Other workloads aren't worth running. So there are a couple of problems with this. One is you can see in this chart that the white kind of represents time that's wasted on those resources, right? Because nothing's running there. And everything above the red line is stuff that didn't make the cut for being worth running on the system, and so doesn't get to run. So those are kind of potentially lost value to the company of analytics that somebody thought were worth doing, but they weren't given resources in the system. So the cloud era brought this great opportunity, right? Because of this promise of resource elasticity, now suddenly everything that was above the cut line, these are potentially new workloads that can be run, and that means that the amount of analytics that can be run in the world is greater. So that's great for companies like Snowflake, but it's really great for our customers because it means that there are these workloads that, like I said, somebody at the company thought had value, but they couldn't run before. And meanwhile, the red spots here, that's potential cost savings, where instead of paying for resources that aren't being used, we can not pay for them because we're renting time on somebody else's servers. So the problem is taking advantage of this elasticity requires the right architecture. So let me now talk a little bit about the options that we had at the time in terms of traditional database architectures. So we've already heard a little bit about the architectural choices for a database system. So I'm not going to go into too much detail, but just to remind you, at the time, there were kind of two main ways to build a distributed database. Shared nothing, which was used by systems like Teradata in the on-prem world, and shared disk, which was used by systems like Oracle in the on-prem world. So shared nothing, the data resides with the node in your distributed system. This is nice for query processing because the data is right there with the compute. It's not so nice in terms of scalability. You're kind of stuck with the number of nodes that you have. If you wanted to add more nodes, you would have to move data around, and that would take a while. Shared disk, maybe it looks a little bit more like something where you could take advantage of the elasticity of the cloud. You have a number of nodes that are reading from a shared storage system. Now, the systems that actually existed at the time were not really built for the scale of the cloud. They were built at a time where network was a real bottleneck. So you needed a very expensive network fabric. You needed typically a very expensive storage system. And you still had a relatively small number of nodes in these systems, and still didn't really have flexibility to scale them out to massive numbers. And the idea of different workloads using different parts of the cluster, while there were capabilities to do that, they tended to be complex and clunky. So Snowflake came up with what we consider a new architecture, though earlier I heard from Andy that it's not really a new architecture. We called it multi-cluster shared data. So in this picture, you can see that it looks a little bit like a hybrid between shared nothing and shared disk. And what I mean by what does it look like shared disk, there's a centralized storage cloud object store in the middle of the picture, which each of these so-called virtual warehouses are accessing. A virtual warehouse inside has a bunch of compute resources, and you can see in the picture that each compute node has its own disk. So in some sense, each of the clusters in this picture are a little bit like a shared nothing data warehouse. So let me take you through a few more slides, and then I'll go into more detail on what all of those things in the picture mean. So Okay, so that's what the sort of compute side of things looks like. There's a separate orchestration layer in our architecture, and this is where requests come in from a client. We have to do things like authorization, authentication, figure out if you have access to this data, figure out what resources are available, what resources are needed for your query to run, and then we send it to our execution platform, and that is the set of virtual warehouses that are accessing the data and the cloud storage. All right, I want to keep it kind of at the architecture level, but there are a few things I just want to point out because they'll be important for some of the topics I discuss later. So the storage tier, we use the blob storage, whatever's provided by the cloud provider that we're built on top of. So that's immutable storage. Each table is horizontally partitioned into a number of what we call micropartitions. You can think of these as files or blobs in the blob storage. We try to keep them pretty small, and I'll talk a little bit about why later. And each partition, like I said, you can think of as a file in the blob storage and is columnar. So it's a hybrid columnar system. And these partitions, it's immutable storage, which is interesting because obviously data is changing throughout time. But these are the unit of change for transactions. So at any given moment, a table state is a set of micropartitions, and then when that table changes through some DML operations, you have a different set of micropartitions that make up the table. We had support for semi-structured data from day one. So we had this variant data type that could basically be schema-less. So you could just drop a JSON document into a variant column, and we would automatically detect common patterns in the semi-structured data and automatically optimize the storage accordingly. And finally, each partition or each micropartition stores metadata, things like min-max values for each column. And this is all automatically collected as you load data. So unlike some systems where there's some sort of process that collects this kind of statistics, this is done automatically. And this is used for optimizations like partition pruning, which is a super important optimization. And we saw earlier how it can really have an impact on how much data you actually need to scan. All right, next up is the compute tier. This is kind of the thing that I think people think about the most and think is the most interesting aspect of our architecture. And this is, as I mentioned earlier, we have this notion of a virtual warehouse. A virtual warehouse is an abstraction to manage a set of resources that are used by a workload. And within a virtual warehouse, we have one or more clusters of nodes. And I'll get to the one or more to the or more part in a moment. But if you imagine you have a cluster of nodes, and these are automatically kind of spun up and spun down as you need them. Warehouses can be different sizes. That's what you see in the slide, that they're different sized. And the range of I can only fit 2 to 4 nodes on the slide, but obviously we can go up to like 1,000 nodes in a cluster. And the size of the cluster kind of varies with the data size. So depending on how much data that you need to process, you would want a bigger or smaller cluster. And I mentioned the or more, one or more clusters in a warehouse. You can also have multiple clusters. And you can think of, varying the number of nodes in a cluster kind of depends on the size of the processing task, so the amount of data or how complex a query that you're running is. The number of clusters is more related to the amount of concurrency. So for instance, if you have a dashboarding workload and you have lots of analysts that are kind of hitting that dashboard over time, sometimes lots of people are using it, sometimes nobody's using it, you might want different number of concurrent queries to be optimized for, and that's what the multi-cluster aspect gives you. So that's what the bottom one shows you, that we have 2 clusters of 2 nodes. The compute is all just in time. So as I mentioned with multi-cluster, you can vary the number of clusters you have, you can vary the number of nodes in a warehouse, and you can vary the number of warehouses. And you pay for what you use. You can configure the system to automatically suspend. This is how most people use it. If I'm using my warehouse, I'm paying for nodes. If I'm not, they go to sleep. And the virtual warehouse has this partition cache, which is super important to getting good performance. This is what lets us get kind of similar performance aspects to a shared nothing system where every node has their cache of partitions, and queries are sent to nodes that are likely to have the data that the queries are running on. And yet at the same time, the nodes have the flexibility to any node can access the data for a table. And this lets us deal with things like skew. This also lets us bring nodes up and spin nodes down, where a new node can load whatever data it needs into its cache. And finally, there was this third piece that was in the diagram, which I mentioned as kind of the orchestration, authentication. From a query processing perspective, this is a little bit less interesting. From a value to customers, this is a very interesting tier of our system. This is the part that does most of the self-managing of the system. And what I mean by self-managing is customers don't need to upgrade data or upgrade their system. We automatically upgrade the system for them. This is done, typically once or twice a week. This is also the tier of the system that figures out if something in the system's unhealthy and we need to replace nodes. Because unlike in a big bad on-premises data warehouse system where you have kind of high quality, expensive components, in the cloud you don't necessarily have as reliable of components. And so this part of the system basically looks at every component of the system. If something's not working, take that node out of circulation, put a new one in. Likewise, it figures out how customers are using the system. Do I need to spin up new clusters? Do I have too many clusters that are idle? Do I need to spin them down? So this is kind of the control plane. It does things like manage all of the connections, manage authorization, things like that. But I think that this self-managing piece is kind of the really critical piece in terms of value to the customer. Okay, so again, we put it all together, and this is our architecture. And this is kind of, it says on the slide, region architecture, which I'll explain in a moment, but this is kind of the architecture as it existed from day one when we released Snowflake. That's actually not exactly true. We didn't have this multi-clustered notion when we first released it, but we added that soon after. Okay, so today, the one big thing I would say that's changed about our architecture since the early days is that when we first released Snowflake, we existed in one cloud provider, AWS, in one region. And over time, of course, we had customers who wanted to operate in regions all across the world, and we had customers who were operating in different cloud providers. So we started building out these kind of region deployments in all of these different regions. And we saw that we really needed a way to make those regions communicate with each other. So that if I have data in one location, in one cloud, let's say I want to have my DR strategy, my disaster recovery strategy be that I can fail over to a different cloud if this region goes down. And so we built this global data mesh, which gives us the ability to have data move between these different region deployments. And I'll talk a little bit about this later. Okay, so putting it all together, these are kind of three kind of pillars that we were optimizing for when we built Snowflake. Unlimited scale, which I already told you a little bit about how that works. I think that this is the thing that most people, when they thought about building a system for the cloud, this is the thing they thought was really important and valuable about building in the cloud. But I would argue that the second pillar, collaborative, is a really cool ability that you get by being in the cloud. Because before the cloud days, data was siloed into organizations' systems. And it wasn't just siloed between organizations. Within an organization, you might have different data warehouses, different data marts that were owned by different organizations. So like coming back to the example I had earlier, finance might have their data mart and marketing might have their own. And if I wanted to ask questions that involved data from both of those, that was nearly impossible to do. So the fact that all of this data is now moving into the cloud opens up a ton of opportunity for being able to collaborate on data. And finally, simplicity. As I mentioned, the self-managing capabilities of Snowflake are super valuable They really kind of shift your mindset about what it means to use a system. And they can get you away from that fear of having to install a database system that we heard about earlier. I'm not going to talk about all of those aspects of self-managing, but I will talk about certain capabilities related to our simplicity story. Okay, so first of all, unlimited scale. So like I mentioned, this is probably something that everyone's already thought a lot about as it pertains to cloud computing and database systems. So there are a bunch of dimensions of scalability. One is that you can have more or less data. As your data size increases, you want to be able to process it just as fast. And this is kind of what I think the original notion of the elasticity of the cloud, how this pertains to database systems, is that, hey, let's say I have a bunch of sales data in my OLTP system, and I dump it into my data warehouse, and I want to do some analytics on it. Well, there are certain days of the year or weeks of the year where I have much higher sales volume, and I don't want to have to wait to get my results for that, right? So let me throw more compute resources at it. So the way that Snowflake allows you to do that is by increasing the size of a warehouse. So you can have anywhere from 1 node to 1,000 or so nodes in a warehouse. You can also have more users of a workload. I mentioned this earlier with the dashboarding use case. But as we see kind of, like I said, more and more data personas, it's more and more common to have less predictability in your workload patterns. So instead of having kind of a team of people that are responsible for all of the data analytics in your company and who do batch processing, they do their load at this time of the day, and then they do a bunch of batch processing, and then there are these kind of pre-canned reports. You have a lot more kind of interesting ad hoc data processing going on. And the way that Snowflake's architecture enables that is this multi-cluster notion where you can basically say, I want to be able to scale up to this many clusters, and you figure it out, figure out how many clusters I need at any given time, and just adapt to the workload. And finally, we have more workloads. And I said this at the very beginning, that there are just different types of data out there, different types of people using the data, and that just means that there's this proliferation of things that people at companies want to do with data. And in that on-prem world where you have this 3-year refresh cycle, if you had an idea for something new that you could do, you would have to kind of wedge that into the resources that were available. And now in Snowflake, you just have these separate warehouses, and you get performance isolation. If I have some crazy new analysis I want to do, I don't have to worry that it's going to interfere with some other workloads that really need to be stable because our business runs on them. And so that's kind of the beauty of these different clusters and different workloads or different warehouses, is that workloads have both cost and performance isolation. So if I want to run my new analytics, I know I'm not going to impact somebody else's workload, but I also know that I can kind of control how many resources are going to that. I'm responsible for the cost of that. Within big companies, you can have different cost centers, and you can attribute the use of Snowflake back to a cost center, which is harder to do. Again, it required this sort of clunky workload management capability in on-prem systems. All right, so back to my very simplistic example earlier, you can see that the green workload, which is probably some type of ETL, load workload, because it spikes and then it goes quiet. It has its own warehouse, and so it wakes up, uses a bunch of nodes, does its work, goes to sleep. And then this other workload, which you can see it's a little bit spiky, but it's a little bit more consistent. Maybe it's some sort of ad hoc workload. That has 2 clusters in my simple example, so that when you hit one of those spikes, you don't have to queue your query and wait for resources. All right, next I'll talk about collaboration, which, like I mentioned earlier, is one of the things that I think we didn't think about too much at the beginning of the cloud era, but I think is actually pretty cool. So I have this little diagram here which shows you how we normally think of an organization having data in their analytics system, and that's kind of at the center. But outside of that organization, there's always an ecosystem of other organizations that they interact with. So this could be your suppliers, it could be your customers. You can imagine, if you're a grocery chain and you collect loyalty card information about the things people are buying, you might want to share information with your suppliers about the combination of products from that supplier that consumers are buying, because maybe that can help them with their marketing efforts. So this is an example of kind of that ecosystem of relationships. And then outside of that ecosystem of kind of direct relationships that you have, there's just more and more data out there that's available for people to use, available for people to buy. There's weather data out there. I like to scuba dive. There's data from all of the buoys that the US government owns going back decades. That's fun to look at and process and figure out where you should go what month of the year. And so, there's even data that people weren't necessarily thinking of accessing before the cloud, but now that's all available. And so people can think of these new ways to take their organization's data and get more value out of it by collaborating with other organizations' data. So how did this happen before the cloud? So in a lot of cases, it didn't happen. But for some of these kind of partner examples that I just gave, it was happening, but it was happening in a very low-tech way. It would be, typically you would unload data from a data provider system. Oftentimes FTP servers were involved. Files would just, be dropped on the provider's FTP server, and then the consumer would kind of pick it up, load it into their system, hope that everything was in the format that they were expecting and the load worked. Hope that the file was on the FTP server in time, and so that worked. So this is, again, very flaky. A lot of companies did do things like this, but a lot of companies just weren't doing this because it was very complicated. It had to be really high value to your business to even do this kind of data sharing and analytics. All right, so in Snowflake, this shows kind of a bunch of data sitting in Snowflake. The provider has some tables right here on the left side, and they decide that they want to share with this consumer. So this is quite easy to do in Snowflake. We have this thing called a share. You create this abstraction called a share. You can say these databases are part of the share, or these tables, or views, because a lot of times you want to kind of give a pre-processed view of the data to the people that you're sharing with. So you package this all up into this abstraction, and you say, I want to share it with that organization. And then, on the right-hand side, we have our consumer, and they can basically query from that share, and they can query from that share alongside of their own data. So this makes it super easy for an organization to basically join in some way their data with this shared data and get more value out of their organization's data. So that was a very simple example. It works pretty easily when you're in the same cloud region. It gets a little bit more complicated when you're across regions. But this comes back to the global data mesh that I mentioned earlier. So the reason that we want to have that mesh, in part, is to aid in collaboration. But we have kind of a similar process where you say, I want to be able to share this to consumers on this other region or this other cloud provider. And then the data is automatically replicated. And you do the same, like, OK, now I'm sharing from that location to another organization. All right. And last but not least, simplicity. So I talked a little bit earlier about simplicity as it relates to kind of managing the infrastructure of your system. But now I want to talk about some of the other kind of higher level simplicity capabilities in Snowflake that our architecture helps us to provide. So I'm going to talk a little bit about automatic optimizations. So I have a couple of examples here. We do several automatic optimizations inside of Snowflake, but I think these examples are ones that most of you are probably familiar with, and so it's pretty intuitive to talk about how the architecture interacts with these optimizations. All right, so I think it wouldn't come as a surprise to any of us that data layout affects query performance. I talked earlier about how we store metadata that allows us to prune micropartitions. We heard about it in some of the earlier talks as well. And so inside of Snowflake, we automatically partition data into micropartitions based on the order that the data arrives into the system. But it might be that you're running queries that are querying along some dimension that has nothing to do with the order the data arrives. So, for example, if you're querying on a date in your data, probably that is actually correlated to the time that the data arrives in the system. But if you're querying on customer ID, if you have customers all across time, probably not very useful. So if you have some dimension that you're commonly querying on, you might want to reorganize your data so that you can optimize for partition pruning along a different dimension. So this is what clustering allows. In Snowflake, we have this capability called clustering where you can specify these dimensions that you want to kind of optimize your data layout for. I have a little diagram here that's, at least for me, an intuitive way to think about clustering. It basically takes a bunch of micropartitions that have data kind of scattered all throughout them, and it converts them into a bunch of micropartitions where the data is clustered along your dimension of choice. So this is all done in the background. And the fact that we have an architecture where you can spin up resources that work independently from other parts of your workload make this background optimization way more achievable. I also, as an example, mentioned file consolidation, and this is basically actually a slightly more simplistic problem to solve. But basically, I mentioned earlier that we try to keep our files relatively small. And this is because it makes it more likely that we can do partition pruning. But there's kind of a tension between having small files so that you can get more optimal partition pruning and having too small of a file. And then there's overhead of metadata management, the header in the file. There are all sorts of reasons that you don't want the file to be too small, or the actual kind of data payload that you get for each file that you process is small, and that overhead overwhelms you. So you want file sizes to be just right. So we also have an automatic optimization called file consolidation, and that takes kind of files that are all over the map in size and converts them into files the size that we like for processing in Snowflake. All right, so how did these kinds of optimizations work in the pre-cloud era? So as I mentioned, these are all done in the background, kind of automatically for you. You as a customer don't have to worry about it. And in the pre-cloud era, you would end up with the background processing and foreground processing competing for resources. And there are a few different ways that you could kind of solve for this. I talked about workload management. You can say, okay, the foreground processing gets this priority. This is very complicated. It was very complicated to get it right. Other systems took a kind of maintenance window approach. And that worked, I would say, at a period of time. But as we had this kind of explosion of different types of data analytics, a lot of it became 24/7, so there really was no notion of a maintenance window. So basically, either of these routes kind of got you into this situation where you might not be able to do the background processing that you need to optimize your foreground processing, which then slows down your foreground processing. And it was all very difficult to reason about. Like, why is my foreground processing slow? Oh, it's because something happened and the stuff that's supposed to run in the background didn't happen. So I have this sort of complicated diagram. It shows how automatic clustering works. But I'm going to skip over it because the key thing to know is that we have this whole process for automatic clustering, and it all runs on Snowflake managed resources. So a customer can have their workloads running in their warehouses. Some DMLs come in. We decide that we need to update the clustering and recluster some of the files. And we can do that in this separate pool of resources owned by Snowflake and not have to worry about fitting it into a maintenance window or doing it with just a little bit of the resources of a customer system. So the fact that we can do this isn't just interesting for clustering and file consolidation. It's interesting for all of the automatic optimizations that we can imagine, which in the sort of on-prem world, you would be hampered by the fact that for all of the great ideas that you had, how many of those could you actually fit into your maintenance window? How many could you actually guarantee would happen? So the architecture supports the automatic optimizations that we have, but it also allows us to do a lot more with automatic optimization now and in the future. Okay, so bringing it all back, our architecture has enabled unlimited scale, collaboration, and simplicity. And I think it would be a good time to take some questions.